So we've talked a few times about really big, massive stars that explode as supernova at the end of their lives. But what about the dinky little stars that exist in our universe?
Yeah, and it's interesting to think about how small a star can actually be before it stops being a star, which is a thing we've talked about with planets, right? At what point something is no longer a planet.
Yeah, so we have an expert today on very little stars and things that are almost planets. Dr. Emily Rice, who's a research associate at the American Museum of Natural History in New York and an assistant professor at the College of Staten Island, CUNY. So welcome, Emily.
Associate now. Yeah.
Associate,
Hi.
all right.
Yeah. And on sabbatical, like, woo! Party!
Okay, so I guess the question comes down to how small can a star be?
It's not too easy to answer. We have like a straight up nice physics answer, which is super, super cool. So the smallest that a star can be is what's called the hydrogen burning minimum mass. HBMM, I guess. We never really use that. Like, we never say HBMM, I don't think. But it is an acronym that shows up in research papers and things like that. So the hydrogen burning minimum mass is the least amount of mass you need to have a high enough temperature and pressure at the core of a star-like object in order to stably fuse hydrogen and helium for a long amount of time.
So, in a very quick summary, what is a brown dwarf?
So a brown dwarf is an object that forms like a star, but then ends up being below this hydrogen burning minimum mass. Notice that I haven't said a number. You're like, because we kind of don't know. It's still a little bit up to debate, and it definitely is going to depend on the exact composition of the objects and things like that. But the hydrogen burning minimum mass is somewhere around maybe 72 to 75 Jupiter masses.
So I get the dwarf part of brown dwarf, but the brown always confused me or always sounded kind of
Yeah.
weird. So where does that come from? Where does the name come from?
Yeah. So originally, this is a super cool thing about brown dwarfs is that they were postulated to exist. Like the physics of their structure was worked out in the 1960s in a couple papers in 1962 and 63, I believe. But in those papers, the author S.S. Kumar called them black dwarfs because it was kind of like they're not stars, they're not shining. But now we understand that they do shine a little bit because they have leftover energy from their formation. So they form and they heat up, and so they have this kind of surface temperature, kind of like the sun. They're usually less than half of the surface temperature of the sun, and then they just cool and fade with time. They don't really get more energy. They don't create their own energy from the hydrogen fusion. And so within about a little over a decade, actually, they were renamed into the brown dwarfs by Dr. Jill Tarter, who is the founder of SETI, a fairly well-known astronomer.
So, one thing that I think is really interesting is I spend my time looking for very, very distant galaxies in very deep Hubble Space Telescope images. And one of the things I have to do is clean out brown dwarfs from my samples because they're also very faint and kind of red looking. I think it's funny how some people's junk is like someone else's science. But they are very, very faint because obviously they're not shining like the sun. So when you're intentionally looking for them, how do you go about finding them?
I think very similar. I think we have to clean out our high Z galaxies in our brown dwarf searches. So we look for them at infrared wavelengths of light because that's where they're brightest. And then we use different ways to look at it. So color cuts, observing them in different filters, and then comparing the brightnesses in different filters. But really, in order to figure out what it actually is, you have to take a spectrum. And then it becomes wildly obvious whether it's a brown dwarf or a high Z galaxy. So the brown dwarf, you'll have these big kind of camel peaks of it's really absorption being taken away from the black body from the thermal spectrum. But the high Z galaxy, from what I understand, is going to be a very low continuum and then a lot of emission spikes.
Yeah, if you're really, really lucky, most of the time we get no emission lights at all.
And so once you take the spectrum, they can look very different. Yeah, but I think we search for them in very similar ways.
And by looking at these brown dwarfs, what do they teach you about stars in general and maybe stars like our sun?
It's important to study the brown dwarfs in order to understand the tail end of star formation in terms of mass. But really where the money is right now is comparing these things to exoplanets. And that's, I think, fantastic because it's true, especially like these So there's habitable exoplanets or potentially habitable exoplanets that a lot of people are interested in. But in order to be really potentially habitable, you have to understand the entire planetary system. And in our planetary system, we have a bunch of massive planets, Jupiter, Saturn, and to a lesser extent, Uranus and Neptune. And that's probably the case in other planetary systems as well. And we can't always find both of those types of planets, the low mass ones and the high mass ones, in different systems. But right now, the planets that we can kind of directly find an image and directly take spectra of to study their atmospheres are massive planets in young planetary systems. And so because of that, they have those exoplanets have a higher temperature, and the temperatures actually overlap with the temperatures of brown dwarfs. But the data that we can get for the brown dwarfs are much, much better data than the data that we can get for the massive exoplanets. And so we think their atmospheres are going to be kind of similar, at least to first or second order. And then we can use the brown dwarfs to understand the massive exoplanets. And that's actually a lot of what I do for my research, which is fun.
And where is the line? What's the major physical difference between like a small brown dwarf and a big Jupiter?
I think that one's even harder to answer. Like this one, if you ask astronomers, you're going to get even more different answers. I feel like it's more kind of similar to the Pluto debate even. It used to be that we thought about it also in terms of mass. So there's this lower end of nuclear fusion that happens where, so below 75 or so Jupiter masses, 75 times the mass of Jupiter, there's no hydrogen fusion going on, stable hydrogen fusion at least. But like I mentioned, there is some other, the engine turns over a little bit. There's a little bit of fusion. But below about 13 times the mass of Jupiter, there's really, really nothing. Like that one, you're just going to get a click when you turn the ignition. And for a little while, we considered those planetary mass objects. And in fact, this is why I think, we've kind of changed maybe the history of exoplanet discoveries, because one of the first exoplanets that was discovered was thought to be above this 13 Jupiter masses. And so it was kind of thrown out and ignored. And poor David Latham in Harvard didn't get credit for it, really. But now we understand that actually exoplanetary systems, especially around more massive stars, can have more massive planets than that. And so there's not this, and it really doesn't make sense to have this mass definition or this mass distinction between the brown dwarfs and the exoplanets. What really matters, I think, and I think a lot of people are starting to think, is the formation of the objects. So this is where when I give talks, I put up my Beyonce slide. Because really, a brown dwarf, like I said, forms like a star. It forms like a star, but then isn't massive enough to actually shine like a star. And a planet, I don't think it should be controversial to say, forms around a star. And so there's two really big differences in formation between those two different objects.
So it sounds like size is kind of an easy cutoff, but, not really perhaps a great definition. But the internal engine, how it makes energy, how it formed, that's what really tells you star or not a star. A very boring app, but a very interesting place to do some astro research. So thank you, Emily. Appreciate it.
Thanks for having me.
Thank you.